All right, we're back and we're talking about cross-validation, and we're looking at k-fold in particular, k-fold cross-validation. And we started out, so we were talking about how we wanted to minimize this expected loss, but we don't know the true distribution p, so we can't compute this thing. But what we're going to do is try to estimate it. So we're going to try to estimate this expected loss, this error, epsilon m, for each of the models in our model class, 1 up through C, finite model class. And we're going to do it in the following way. So we took our data D, and for illustration purposes, well, let's suppose that we had 100 points in it. We randomly permuted it. We split it into these k equally sized parts, or roughly equally sized parts. And here we were assuming, for illustration purposes, we were assuming k equals 5, just to make things nice and concrete. But in general, this could be some arbitrary integer k. Well, it has to be less than n, I guess. And then we were writing down this matrix to visualize the cross-validation process. So the process is the following. So here's what we're going to do. For each m, and this is for each m from 1 to C, for each of our models in our model class, we're going to train it using only, so for the first round, for round 1, for a particular m, we're going to train it on folds 2, 3, 4, and 5. So we're going to take all these and lump them all together into one training set. So if n was 100, this has 80 points. And then we're going to evaluate it on the validation set, which for round 1 is fold 1. So we get, for some m, we get some estimate. Let's call it epsilon hat sub m of 1, so it's for the mth model, and it's 1 because it's for the first round. And then we forget everything from the first round, and for the second round, we start over. We say, okay, we're looking at model m, and we're going to take now fold 1 and lump it all together with folds 3, 4, and 5. And we'll use that as our training set. We'll construct a prediction function or classifier or regression function or whatever using that as our training set, folds 1, 3, 4, and 5. And then we'll evaluate it on fold 2. So that's for round 2. And that gives us epsilon hat sub m of 2. And then we do the same thing for 3, 4, and 5. We get epsilon hat m 3, 4, and 5. And then we put all these together. We average them all up together into epsilon hat m. And that's just the average. So it's 1 over k times the sum as I goes from 1 to k, epsilon hat m of I. Just the average of each of these. So it's averaging the error, the empirical error on each of these different rounds. And then the last step in the process, step 4, we choose m to minimize epsilon hat m. So you choose the model in your model class that has the smallest estimated error. So this gives you an estimate of this error, right? This was epsilon hat m. This is an estimate of epsilon m, the true error. And that is cross-validation. Oh, and I guess, well, there's one more step. So you would choose m to minimize this, and then for your final thing, you would retrain using m. Maybe this is like, we call this m star is the minimizer. and we would retrain using M star on all of D. So we would get our final classifier or prediction function by using the best model, and we would, training it on all of the data. And that's cross-validation. So one question here, one thing which we haven't really talked about, is how do you choose K? What is the good value of K? Well, so I'll come back to it a little bit later. We'll talk about what is a good value of K. Often, let me just say at this point, oftentimes people use either 5 or 10 for K. But another very popular choice is to use, so that's the end of cross-validation, the general setup, the general thing. But another, rather than using 5 or 10 for K, a popular choice, so we had A, remember this was, so A was validation, we just took one split. B was cross-validation, or K-fold cross-validation, and that was we took these each of these K different splits, and we evaluated on each of them. And now for a third option, well, it's really, I guess, a special case of B. Special case of cross-validation is leave one out cross-validation. Leave one out cross-validation. And this is just K-fold cross-validation when K equals n, little n. K equals the number of points. So what is this doing? This is doing, right, so that we've got, back up to our data here. So for leave one out cross-validation, each point itself is a fold. So we have n folds. Each point is one fold. So at the first step, and in the first round, we're going to have n rounds. In the first round, we train on, well, I guess we permute everything first. But actually, for leave one out, it doesn't even matter. So you don't need to permute. But so we would take the first one as a validation set in round one. We would train model M on all of the rest, 2 through n, evaluate it on this one, and that would give us our first, epsilon hat 1, epsilon hat M of 1, and then we would take the second one. So I think you get the point. You see the idea. So you take K equals n. So you have n folds. Each point is a fold. And that's leave one out cross-validation, sometimes fairly popular choice. So let me tell you about one more option along these lines, D, which is closely related. And this would be random subsamples. And for this type of method, for this type of cross-validation, I don't know if you really call it cross-validation. It's really a little kind of different. You again have a sequence of rounds. So we have round 1, 2, 3, 4, and so on, up to some, I don't know, capital R number of rounds. And in each round, so in the first round, you choose a random subset, just like the name suggests. You choose a random subset of size, let's say, size S. So S is a parameter here. So you have, before in K-fold cross-validation, we had this one parameter. We had the parameter K. Of course, I mean, there's all the parameters in your model and everything, but for the procedure, the model selection procedure, there was this parameter K. And now for random subsamples, we have the S parameter and we have the R parameter. How many rounds we're going to do and how big each subset's going to be. So in round 1, we would choose a subset of size S and take that as our validation set, and the rest as our training set. And then it's just like before, you get some for each M, you get some number, epsilon hat M of 1. And then the second round, you choose a different random subset of size s. You get epsilon hat m of 2, and so on, up to epsilon hat m of r, right? And then you just average those like before, and you get your estimate of the error. And that's called the random subsamples method. So let me briefly say a comparison between random subsamples versus cross-validation, pros and cons. In cross-validation, one advantage to it is that you're using each point here is used for validation an equal number of times. In fact, it's used exactly one time. Each point is used exactly one time for validation. So it's sort of, equally distributed according to, maybe if there was like a super hard point, maybe this one was like super hard, point, I don't know, 19 was super hard, you're only testing one time on that. But down here in the random subsamples, if you like here, if I chose this point twice, maybe this was that hard point 19, and that was part of my validation set in these rounds, I might end up by chance choosing that a bunch of times, and then I would be overestimating my error if I did poorly on that hard point. So that's something which is maybe more attractive about cross-validation. But a disadvantage of cross-validation is that you can only do that, the number of rounds you do is equal to the number of folds, and each fold, like if I have k folds, like then I have to divide my divide my whole set D into k equally sized parts. So, it sort of introduces this strange dependency between the number of folds, the size of my training and validation sets in each round, and the number of rounds. Whereas we might want to choose maybe a smaller training set and larger validation set, or a larger training set and smaller validation set, and have a different number, maybe have more rounds in order to get a better estimate of the error here. And so that's an advantage of the random subsamples method, is that you can choose these independently. You can choose the size of each of your validation sets, and you can also choose the number of rounds. So that's a nice thing. But just like I mentioned before, there's this sort of dependency between the different rounds, because you could, of course, the whole thing is always the same set, so you're going to be reusing certain points multiple times or for training, and reusing them multiple times for validation in the random subsamples thing. So there's this sort of strange dependency there, which does not show up in cross-validation, because each point is only validated. You're only testing, it's only part of the validation set one time, so you're only testing it one time on each point. Okay, so that was a little comparison between these two, and introduction to these main different types of cross-validation. And I'll have to stop there because I'm running out of time, but I do want to tell you how to choose K for cross-validation. So we'll come back to that, and we'll talk also about a couple other issues associated with cross-validation. Okay, we'll be back in a minute.